Okay. With the changed circumstances, probably our class routine will go on changing. Till today, we will follow the earlier routine. Uh, but later on, from tomorrow, it will be a different one because probably you have to go to the college for your lab classes and all. Maybe you have received the notification, I guess. You have you? Yeah, okay. So are you all the groups are you coming tomorrow for your lab classes, your respective lab classes in the department or maybe elsewhere?
No, sir. We are coming on Thursday. Half of our class is coming like
Okay.
tomorrow, and the other half is coming on Thursday.
Right, right. Okay. Okay. So I actually, I also have lab classes, our departmental lab classes that in mechanical engineering tomorrow. Those who are there tomorrow, we would like to see you, but then tomorrow's my schedule is from 9 o'clock to 5:30. All the four labs will be taken. Actually, each experiment has to be done twice because we are taking the classes with reduced half the strength. Earlier, we used to have 30 as a lab class strength. Now it is reduced to 15. So for each experiment, we have to repeat twice. Anyway, so I would be there, uh, not necessarily that because there will be some restrictions of moving around and all. Therefore, I would not like to physically. I would love to see you physically, but then never mind. I mean, you carry on with your schedule. We will meet sometime. Let us let us discuss about this class as usual. We shall recap of the previous class. We will do
So,
then growth
so,
mathematics. Yeah, yeah, please.
so last class you had talked about creating a Google Classroom for sharing the notes and everything, and you said that you'll share the
I
link
have
with us.
I have created a classroom. The only thing is the link I have not shared with you. This link I shall share with you, and also the lecture notes will be uploaded there. I shall be uploading. Only thing is that my scribbling is actually this needs to be a little faired up. I mean, একটু ভালো করে লিখে and then I will upload this into the then only it will make sense. You don't have to whatever I give. If you read this, as far as the exam is concerned, you won't have much of a problem. Of course, you can refer to many books.
Okay,
So
sir.
you just give me a little time. Maybe day after tomorrow, I shall give you the invitation. Also, I shall upload whatever notes I had written in that. उसको फेयर करके मैं उसमें upload कर दूंगा. Okay.
Okay, sir.
So today, what we will discuss a little more about the growth maths. Actually, we in the last class we talked about the growth mathematics, about exponential growth and all. Today, we will also take out this class in the growth mathematics. What we will discuss is called half life. For example, when something is growing at an exponential rate, there may be something which will be decreasing also, decaying also at the same exponential rate. So, for example, if the coal production, um, if we are thinking of the production, increase of production per year, exponential rate of production, on the contrary, you can also define it as a depletion of the coal reserve. In other words, if you the production rate is also associated with the depletion of your reserves already you have. So you can also calculate, provided you know the uh, quantum of coal that is reserved. So how much time it will take for the for this earth, for that fossil fuel to survive, how many years. So this can also be done. So when the rate of decrease of quantity is proportional to the amount present, we we will call it exponential decay. So we write when the rate of decrease of quantity. This quantity may be coal.
Sir, your
This may
writing
be.
is not visible properly. Please
This may be.
focus your phone.
Yeah, I know, because actually it is not illuminated properly. Yeah, I actually this particular, we have a proper, because it's the overcast. I am just sitting by the window, but then this is all I can do. I mean, you have to bear with me. Yeah, I'll send the class notes in any way. When the rate of decrease of quantity is proportional to the amount present, is proportional to the amount present, we call it exponential decay. Exponential decay. And the same formula, n is equal to n0 into e to the power minus kt. This is the equation. In that case, where k is equal to rate coefficient n0 is equal to initial amount. It may be money, it may be coal reserves in tons of coal, it may be amount of production, initial amount, and n is the amount decreased in time t. So if you plot this curve, it will be, if you plot this curve, so we have started from the point n0, and the exponential decay, it is happening like this. So this half-life we shall discuss at n0/2. And the quarter, that means this is the axis, this is t, time, and this is the n. Now this, the equation of the curvature is n is equal to n0 e to the power minus kt. This is the half-life. That means this point is t half. You can also calculate t 1/4 further half, that means n0/4, and this will be double the amount of tt, that means 2 into t half. This is the point t half, and this is 2 of t half. Now, so from the equation 1, n is equal to n0/2. Therefore, n0/2 you can write is equal to n0 e to the power minus k t half. Therefore, T half-life period. Half-life period is very known term for you because of the radioactive element you have studied in the class 12. So T half is equal to, you will find that it is ln2 divided by k, and ln2 is 0.693 divided by k. So if you know the rate, so T half can be easily calculated from this equation. That means there is a constant term called 0.693, 69.3% divided by rate of the rate coefficient. If you divide, you get the half-life period. Now we will discuss what is called I'm sorry, really, I mean this, in fact, I myself is having a problem with such a low illumination, but there is a problem out here. The next is page number 2 plus. We will discuss disaggregated. Disaggregated growth rate. What exactly does it mean? Disaggregated growth rate. Sometimes the quantity which is to be projected in future can be considered as a conglomeration of a number of individual factors. I repeat. Sometimes the quantity which is to be projected in future, time and again we have to project. If this is the rate of the growth, if this is the rate of the depletion of the coal, if this is the rate at which we are emitting carbon into the atmosphere. So, till how long we will survive in this planet, or the survive in the planet in the sense that provided all other remains constant, how much ozone depletion will take place, how much time we have till the coal is finished, like that. So this aggregated growth rate is sometimes this project is it may be a conglomeration of a few factors. For example, okay, let us write. Sometimes the quantity to be projected in future, quantity, forecasting technique. Sometimes the quantity to be projected in future can be considered to be the product of a number of individual factors. For example, let's say example. We all know that the emission will take place, the amount of carbon emission that will take place will depend on the population. So let us say carbon emission is equal to a factor of, say, population, or rather function of population. Then you have a energy per person, energy per person, and it may be, and carbon per energy is a factor of this one. Or in other words, you can write carbon emission is equal to population into energy per person into carbon per energy, right? More number of population, more of energy is required. Now, once again, energy per person can be defined as your affluence. Energy per person can also be taken as, see, we can write population into energy per person is a term called affluence. Short question. Energy per person is called affluence, and carbon per energy, this is basically carbon per energy. You can also say that this is technology. Because this carbon per megawatt of energy production, carbon emission, because human beings are now these days, they are aware of the carbon emissions, and they are making such procedures, technological advancements also, how to reduce the carbon emission into the atmosphere. Therefore, it is expected that the as the technology improves, the carbon emission also is getting reduced. So we can say that the carbon emission is a product of population, affluence, and technology. So carbon emission is the impact. Therefore, we can write impact is equal to population into affluence into technology. Affluence, that means per capita energy consumption. It is directly proportional to the what do you call to the affluence of a particular country. For example, if you take Indian context or US context, you can Google it, you can find out the per capita energy consumption in US is much higher than in India. There are various factors. Number one, US is an affluent country, developed country. Therefore, they have got the economic condition there is much better than in India. In India, people cannot afford also. Therefore, the term affluence comes. The more amount of power per person used is termed as affluence, and carbon emission per energy unit is the technology. So this is the impact. Now let each factor, let each of the above factors grow exponentially as given below. Let's say Pi is equal to so there are many factors will be there. So therefore, the number of factors, say P1 into P2 into P3 into Therefore, Pn. In general, we can write, in general, we may write Pi is equal to Pi into e to the power Ri into t. So if these are the three factors, we can write, therefore, we can write P is equal to P1 E R1 T into P2 e to the power R2 T into P3 e to the power R3 T. So we can write, yes, sure. Yes, right. Now so P1 into P2 into P3, and you go on writing, it will be Pn e to the power Rn T. So P1, P3, P2, P3 dot up to Pn, and this will be e to the power R1T or rather T को common ले लो, it will be R1 plus R2 plus R3 plus dot plus Rn. So finally it will look like this. P is equal to this one, we can write that as a P0 and e to the power R into T. Comparing this, we have R is equal to where P0 is equal to P1 into P2 into P3 Pn, and R is nothing but R1 plus R2 plus R3 Rn. Therefore, from this we can, what is the conclusion? Conclusion is that if a quantity can be expressed as a product of factors, each growing exponentially, then the total rate of growth or decay is the sum of the individual growths. This is the sum of the individual growths or decay, whatever. So we can write, if a quantity can be expressed as a product of factors, each growing exponentially. This is important. Each growing exponentially, then the total rate of growth is the sum of the individual growths. we take one small problem. This is a problem. Energy demand is a function of population, GDP per person, and energy per GDP. These are the three factors. Energy demand is a function of population, GDP per person, and energy per GDP. GDP, all of you, I think you know, gross domestic product is an economic term which signifies the growth rate. GDP growth rate is high, means it is the economy is growing at a fast pace. So GDP per person. Now given GDP growth rate is equal to 2.3% and population growth rate is equal to 0.6%. Calculate the energy demand assuming energy by GDP to decrease at a rate given by the following data. In 1995, the year 1995, this the price was 13.45 kilocalorie per rupee, and in 2005 it has reduced, because of the technology, it has reduced 11.35 kilocalorie per rupee. This is the rate. Now we have to calculate solution. We know n is equal to, this is our growth rate formula, n is equal to n0 e to the power rt, n by n0 is equal to e to the power rt. Therefore, rt taking log, you have ln n by n0. Therefore, r is equal to 1 by t into ln n by n0. Now this is t is equal to T is equal to 95 to 2005, that is 10 years. So therefore, R is equal to 1 by 10 into ln. What was it? In 2005, it was 11.35. 11.35 divided by 1995, it was 13.45. 13.45. You will always find that this will be negative. ln 11.35 divided by 13.35, this will be negative. Therefore, R is equal to, you will find that this is 0.017, means is equal to 1.7%. That means this energy demand is a function of population, GDP growth per person, energy per GDP. GDP growth rate is given, population growth rate is given, and what is not given is the other factor, energy per GDP. So that we have calculated now. Now, overall growth rate then, just we had discussed the overall growth rate is the sum of the individual growth rates. Sorry, this is minus. This is minus 0.17. This is minus 0.17. So therefore, hence, overall energy growth rate is equal to sum of, just now we have derived that equation, sum of all the individual growth rates, sum of all three individual growth rates. That means we had 0.6% is the population growth rate. Then we had GDP growth rate at 2.3%. And due to technology, we had a reduction, which is 1.7%. So is equal to, it became 1.2%. Here, one data was missing. If the let demand in 2005 was 100.2 megawatt. What is the projected demand in, what is the projected demand in 2020? So therefore, demand in 2005 was 100.2, hence the demand in 2020, that means for 15 years, it has to be so it will be the equation is n0 e to the power kt. So n is equal to n0 e to the power rt. The r is this is the r. Therefore, n is equal to 102 into e to the power 0.012 into number of years is 15. If you calculate, it will be 120 20 per year. So what we have done is that when the growth rate is a product of three factors, and two factors are already given, another factor we had to calculate based on the data provided. Based on the data provided, we had to calculate, and then providing that formula that the R is equal to the quantity can be expressed in the product of factors is each growing exponentially, then the total rate growth is the sum of the individual growths. Now sum of the individual growths means there are two growths and one decay. Two growths and one decay. Human population is growing, the GDP is also growing, but due to technological advancement, there is a decay in that factor. So ultimately, we find out the overall growth rate factor, taking into account the decay factor, and then we calculate using the formula n is equal to n0 e to the power rt. Okay, so this is the now with this there is a we have not calculated, we have not taken into account the factors that abruptly changes the world environment. Because you see, we have already, I have already taken the year 2020. In the year 2020, we had a drastic environment change all over the world. So therefore, all these things will not be applicable to such disaster. However, there's a very interesting phenomena we must discuss, that the bacterial growth, I mean, how does it affect and what is the curvature of this population growth? Population growth and the related terminologies we need to discuss. This is called logistic growth. Logistic growth is mathematically modeled as a S curve. S curve. How does it look like? It looks like this. This is time. We shall define the axis later on. So it will be like this. Then there is an exponential growth. Then there is a stationary period. And then there is death. This is typical growth of a bacterial population. In this, you can write log of organisms per ml in this axis, and this is the time. So you will find there is four distinct reasons. One is this one, another is this one, so the third is up to this point, and fourth is this. So this is called lag. This zone is called lag. This is exponential growth, which happened during the period March 2020, exponential growth. Then there is a stationary period. Stationary. And then there is a death. This is the death period. What happens is that when it comes initially into the environment, there is a initial phase is called the lag. Once it is exposed to the atmosphere, then there is an exponential growth. This is the exponential growth. Then after some time, there is a stationary, it remains stabilized. And then it doesn't sustain, and then finally it dies somewhere here. So there are four distinct reasons. It can be this is called the logistic growth of typical growth of a bacterial population, where this the equation for this is dN by dt is equal to R into N 1 minus N by K. What is it? Where N is equal to population size, K is called carrying capacity. Of the environment. R is equal to exponential growth rate. This is all. So you have to apply this equation, and page number 3 plus page number 4 plus page number 5 minus, this will probably be the last page. So this is called the logistic growth, and this is the model of any bacterial typical growth curve of a bacterial population. So I think with this I will not touch upon any more new ventures. Let me see what was my agenda. Agenda was growth, half-life, yeah, okay, fine. So now in the last class, we also discussed about certain things like renewable energy, what is definition of renewable energy, and the conventional energy, renew, all these things. And then, in the case of the conventional energy sources, the conventional energy sources means typical coal-based thermal power plant or fossil fuel-based thermal power plant. The majority of the emissions, majority of the emissions are being given out by the thermal power plants, coal-based, typically the coal-based thermal power plants. Coal-based thermal power plants actually emit carbon dioxide, carbon monoxide, depending on whether the combustion takes place fully or partially. If it is a partial combustion, then too much of carbon monoxide is being formed, which is emitted into the atmosphere. This is dangerous. If you the incomplete combustion may be due to various factors. Incomplete combustion may be due to improper or not improper, stoichiometrically incorrect supply of oxygen into the coal. It's a very complex phenomenon actually, because in order to burn carbon, you need to give sufficient amount of oxygen. As the coal is being injected by the coal injectors into the boiler of a thermal power plant, there is a rapid fire has to take place. In order to achieve the complete combustion, you have to have a multiple factors of, that means the boiler draft has to be proper. Draft is basically the pressure difference between the outside of the chimney and inside of the combustion chamber. What is the pressure difference is called the draft. You cannot, by natural draft, you cannot probably give the sufficient amount of oxygen, or sufficient amount, not oxygen basically, or sufficient amount of air into the system. So therefore, due to various factors, like so many other factors are also there. The degree of crushing of coal, that is also one of the important factors. Degree of crushing of coal. The coal is basically, it has to be pulverized before it is injected through the nozzles into the boiler. So therefore, the degree of pulverization is also an important factor as far as the production of carbon monoxide is concerned. Therefore, there will be these emissions actually take place. As the technology improves, we try to reduce it. And so regarding all these emissions and contaminants, the acid rains and other things we shall talk about in the next class. Please keep checking your mails. Probably tomorrow probably I will have a great clear picture as to whether we will have a theoretical class at what time and all. I shall have a discussion with my HOD and the department of your concern, and then we will let you know, apart from the lab classes, whether the theory class will also go on or not. Thank you very much for attending the class. We'll see you next. Keep checking your mails. By day after tomorrow, I hope to upload all the lecture notes that I have provided, that I have done so far, and I'll send it across to you. Have a good